Good morning, guys. Hope you're doing well. So today we'll try to complete this this section of graphs of polynomial functions. And just to remind you that if you have a polynomial function of degree n and you want to identify the zeros and the multiplicities, then I hope you remember that if the graph crosses the x-axis and appears almost linear at the intercept, then its multiplicity, then it has a single zero. What that means is if it crosses the x-axis and then it appears, that's the y-axis, if it crosses the x-axis and it appears linear, then it has a single zero, or its multiplicity is just 1, because it crosses the x-axis at just one point, and it's a single zero because that, just like I've been saying, if for example that value is -1, then the multiplicity will be 1. If it touches the x-axis and bounces off, this is review from yesterday, then it's a zero with even multiplicity. We're using the word zero to mean that it's a root or that it cuts the x-axis, because everywhere it cuts the x-axis is called a zero. So if it bounces off the x-axis, if say it came and bounced off the x-axis like this, then that zero or that root or that x-intercept has even multiplicity. If it's a zero with odd, if it crosses the x-axis at 0, then it has odd multiplicity. If it crosses the x-axis at a 0, sorry, not at 0, at a 0, and it's crossing the x-axis, so crossing is kind of coming and then doing that sort of wiggle, then it crosses the x-axis, so doing that, then that is odd multiplicity. And just to remind you that the sum of all the multiplicities for a polynomial is going to be equal to the degree of the polynomial. So if a polynomial has a degree of, its leading term has a degree of 5, then the sum of the multiplicities, the sum of the power 1 and the power 2 from here and the power 3 from here, the sum of those multiplicities for that polynomial must equal to the degree of the polynomial. Alright, so question: do all polynomial functions have as their domain all real numbers, or is the domain of polynomial functions all real numbers? You can pause the video before I display the answer, but yeah. So true answer is yes, all real numbers are in the domain of polynomial functions because they are smooth functions and they just keep going because they're continuous. So talking about zeros and turning points, again, I must have misspoke about this in yesterday's video. If a polynomial has degree n, then it will at most have n x-intercept. At most means either the x-intercepts will be equal to the degree or less, they can't be more. And if it has a degree n, then its turning points will be n-1 at most. So if you look at this polynomial, it has 1, 2, 3 x-intercepts, and then it has 1, this is a turning point, this is another turning point, those are 2, this is another turning point, those are 3 turning points. So since it has 3 turning points, and I know that the degree n must be greater than the turning points by 1. So if the degree is n, this is the degree is n, then the turning points must be n-1. So if it has 3 turning points, if the turning points are 3 that I've counted, they're n-1 and they're 3, that means the degree must be at least 4. The degree of the polynomial is going to be 4. And when we check with what the graph looks like and how many x-intercepts we're getting, we have 1, 2, 3 x-intercepts. Is that consistent with what we know about the x-intercepts? Yes, because the x-intercepts have to be at most equal to n, but they can be less than that. And this is also true because even functions, I hope you remember that even functions have their end behavior like this, especially if a function has an end behavior like this, and if it's symmetric about the y-axis, it's usually an even function. So this kind of works with what we expect. An example is here. If we want to find the maximum number of turning points of each polynomial function, then first we arrange it in descending order of the powers. So this one is the same as 4x to the power 5 minus x cubed minus 3x squared plus 1. And when I look at the leading term, the first term of the polynomial, it's 4x to the power 5. I can see that the degree is n is equal to 5. So if the degree is n is equal to 5, I know that the x-intercepts or the zeros or the roots are at most 5. So the x-intercepts will be less or equal to 5, and the turning points will be at most 4, because remember the turning points are n minus 1. And for this one here, b, I don't have to expand this out at all. I'm only interested in the leading term of the polynomial. So I can see that the leading term is going to be the one with the highest power. The highest power from this bracket will be x squared, and the highest power from this bracket will also be x squared. Actually, the highest term from this bracket will be negative x squared, and it's going to multiply with the highest term from this bracket, which is 2x squared, and my leading term will be negative 2x to the power 4. So since I have my leading term, I know that's a graph that will look like this. I will explain that a little bit more when I talk about end behavior of these functions. So the degree is 4. That means that the x-intercepts or the zeros are at most 4 x-intercepts, and the turning points are at most 3, because they have to be n minus 1. Right, so sometimes you're going to be given a function, the polynomial function, the equation of the function, and you'll be asked to sketch it. These look like a lot of steps, but we're going to break them down simply so that you can appreciate them better. So 1, you're going to find the intercepts. 2, you're going to check for symmetry, see if it's symmetric about the x or the y-axis. This is something we talked about in Unit 1, symmetry of graphs. Check if it's symmetric about the x-axis or about the y-axis. 3, use the multiplicities. Remember, multiplicity is how many the degree of the factor at the x-intercept. So check that multiplicity to determine the behavior of the polynomial at each of those x-intercepts. Then determine the end behavior by looking at the leading term. Talk about that a little bit. Then use the end behavior at the intercepts to sketch the graph. Check that your turning points does not exceed 1 less than the degree of the polynomial, and then you can use your graphing calculator to check whether your graph is correct. Let's look at an example about this. So we have a polynomial whose equation is this. F of x is x minus 1 cubed, x plus 3 squared. If I want to graph the polynomial function on here, first of all, I'll find the intercepts. Now I know that for the x-intercepts, I'll find them by setting the function to be equal to 0. If I set this function to be equal to 0, x minus 1 cubed, x plus 3 squared, if I set that equals 0, then I'll just be solving for each of these parentheses using the 0 property. So I'll see that either x minus 1 cubed is equal to 0, which will give me x is equal to 1. You can work it out. Or I'll have x plus 3 squared is equal to 0, which will give me x is equal to negative 3. So my two x-intercepts are x is 1, y is 0, and x is -3, y is 0. So I'll go to my graph and just mark off those x-intercepts. One is over here, x is 1, y is 0, and the other one is x is -3, y is 0. Okay, so those are the two x-intercepts. I need to also find the y-intercept, and I hope you remember that at the y-intercept, the value of x is equal to 0. I just need to set x equals 0 in my function. So I'll basically be looking for the f of 0. So if I set x is 0, I'll have 0 minus 1 cubed times 0 plus 3 squared, because I'm setting x equals 0 in this position in my function, in my polynomial equation. So this will give me -1 cubed, which is -1 times 3 squared. 0 plus 3 is 3 squared, which is 9. So my y-intercept is -9, and that point is x is 0, y is -9. So that point is 1, 2, 3, 4, 5, 6, 7, 8, 9, somewhere down here. I know those are my intercepts. So I've done step 1, not done. Let's go to step 2, check for symmetry. Is this function going to be symmetric? I can check by looking at the leading term. So when I look at this function, I can see that the leading term in this parenthesis will be x to the power 3, and the leading term in this parenthesis will be x to the power of 5. So x to the power of 2. So x to the power of 3 times x to the power of 2 gives me x to the power of 5. So my leading term for this polynomial is x to the power of 5. It has a degree of 5, so I'll expect something less than 5 in terms of turning points, and either 5 or less in terms of x-intercept. But this also tells me that it's an odd function, and it is going to be symmetric about the y-axis. So that's what I expect. I expect a shape that's around this, because it is an odd function. Or not to mislead you, I expect a graph that has a shape that continues that way and continues that way, its end behavior. So we'll see how it turns out in the end. Alright, next step is I want to check to use the multiplicities of the zeros to determine the behavior of the polynomial at the x-intercepts. Remember, my x-intercepts were 1 and -3, and the y-intercept was 0, -9, somewhere down here. So at x is equal to 1, you can see that the multiplicity is 3. You can see that the multiplicity is 3, so at that point I expect the graph to look like this. I expect the graph to cross the x-axis in this way. At x is equal to -3, you can see that the multiplicity is 2. Up here you can see the multiplicity is 2, so I expect the graph to bounce off the x-axis like that, or like this. It can bounce off the x-axis like that or like this, depending on what the other points of the graph are and what the general shape of the graph is going to look like. So this one also, it could cross like this, depending again on what the other points are on the graph dictate my shape to be. Alright, so step 4, determine the end behavior by examining the leading term. I think we've already seen that the leading term is x to the power of 5, and a little hint about end behavior. So for even and odd polynomial functions, if the coefficient of the leading term is greater than 0, let me write this better. If the coefficient of the leading term is greater than 0, if a is greater than 0, then an even function will look like this and like that, where this is the x and y axis. Its end behavior will look like that, as you see in that little sketch. And the odd function, its end behavior will be towards that way and towards that way. This means that as x goes up, y goes up. As x goes down to the negative infinity, y still goes up. This one is the opposite. As x goes up, y goes up. As x goes down, y goes down. If the leading term, if the coefficient of the leading term is less than 0, that's if it's negative, then for an even function, it's going to do the opposite of what it did for when it was positive. So we'll go up and then down that way. As x goes up, y goes down, and as x goes down, y still goes down. For an odd function, it's going to flip such that its end behavior is dictated by that. So for this function, I know it's an odd function and the leading term is positive, so I expect its end behavior to be I expect its end behavior to be something like this and that. That's what I expect. Okay, so I have everything I need. I just want to sketch a graph. So start with this. I have an intercept here, I have an intercept here, and I have an intercept of -9. I know that at x is equal to 1, which is this point, it crosses the axis. So remember, it crosses the axis either like this or like that. You're going to choose depending on what the shape of this graph should be. And then at x is equal to -3, it's bouncing. This is at x is equal to 1. At x equals -3, it's bouncing off the graph. It's bouncing off either like this or like that. Again, depending on what your shape should be. Now, the end behavior of this function, I expect the end behavior to be like this because I have an odd function. I expect the end behavior to be like that. So for the end behavior to be like that, the bounce here cannot look upwards. The bounce there cannot look upwards because if it does, I'm never going to get this end behavior. So the bounce there should look downwards. First of all, if the bounce was upwards, A, you would never get this end behavior, and B, there's no way your graph would go through this y-intercept. So since this helps my case because I know that will connect to the end behavior, this will come down and then go through this point. I'm trying to be very accurate here. Then it will go through this point. You can either curve it here or you can have it curve it up to after this point, since it is just a sketch. We know, however, that this curve will still come and have an end behavior of that and then cross the x-axis at that point like this. So it doesn't matter how you join it, as long as you join it right. I'm struggling here. Yeah, so I've crossed the x-axis, then I come to my y-intercept. Sort of, you guys can do better art than this, but my graph is going to have this kind of general shape. I drew the same graph on a graphing calculator, and I'm just realizing how different mine is from the actual thing. Yeah, so the point that I didn't consider or didn't put into consideration is the symmetry of this function. I hope you can see the symmetry of this function is around about the y-axis, which symmetry is also not very clear on this one, but its starting point is it's between -3 and 0, and that's something that I didn't put into consideration. But since you're sketching, there's really no way for you to know where the turning point is exactly. So yeah, I think you would have just eyeballed this one to make a good shape like that. I have the general shape of the graph, I just have it way off. So since you're sketching, you're not going to be penalized so much for what your sketch looks like, and the ones that we give you to try and sketch will not be as complicated as this one. So yeah, this is what the graph looks like. One thing that I got right was the end behavior. The end behavior, that was right. the shape of the graph at the intercepts, that I also got right, and still that was through prediction, and I also got the y-intercept. So those are the gradable points, and so yeah, I'm just trying to console myself about the fact that I've got this one totally misread. But yeah, that's how you sketch a graph of a polynomial function. Alright, so I want you to try this one, follow the steps that we've discussed, that I've gone through, and then try to sketch the graph of this function. You can pause the video and then try it out on your own. So sometimes you're going to be given information about a polynomial, and then you'll be asked to write its equation. So for example, this polynomial has zeros. Remember, zeros mean x-intercepts. At x is equal to 5, x equals -2, and x is equal to 1. And the y-intercept is at x is 0 and y is 6. So they've not told us anything about the multiplicities of this function. So yeah, they've not told us anything about the multiplicity, so I'm just going to assume that each of them has a multiplicity of 1. So since remember, if x equals -5 is a 0, or is a solution, or is a root, then that means that x plus 5 is coming from the fact that x is going this way. X plus 5 is a factor, right? A factor of that polynomial. Then that also means that since x equals -2 is a root, that means x plus 2 is a factor. Again, the 2 is going over that way. And finally, since x equals positive 1 is a root, that means x minus 1 is a factor. Now, working on the assumption that I have a multiplicity of 1 for each of these zeros, because I wasn't told what the multiplicities are, and it's also consistent with what I expect, because these are 3 factors which would be multiplied to get x plus 5, x minus 2, x plus 2, and x minus 1. I hope you can see clearly that if this is multiplied out, the maximum power of x that you'll get, the leading term, will have a power of 3, and since it has a power of 3, the x-intercepts can be expected to be 3 or less, and I have 3 x-intercepts, or 3 zeros, so I'm within what is correct for this expression. Since it has a y-intercept at x is 0 and y is 6, I can try to figure out a way to manipulate this equation such that when I set x equals 0, the y value is going to be 6. So if I set x equals 0 here, if I set x equals 0, I'll have 5 times 2 times -1. 5 times 2 times -1 is -10. So you're asking yourself, what factor do I need to multiply with this -10 such that my y value is 6, because the intercept is at 6. Alright, so you're simply solving that simple algebraic equation, 6 equals -10n, and you see that n is going to be 6 out of 10 negative, which divided by 2 is 3 out of 5. So your final expression is going to be y is equal to -3 out of 5, x plus 5, x plus 2, and x minus 1. If my handwriting looks terrible today, it's because I'm trying out this new sketchpad and I'm getting used to it slowly. So using this expression, if I set x is equal to 0, my y-intercept will be 6. And if I solve for each of these, I'll still get zeros at -5, -2, and +1. So that's how you can find the equation if you're given the information about the graph. If I had been told what the multiplicities of these are, if say I had been told that this has a multiplicity of 2, I'll just put a squared on top of the x plus 5. Alright, extrema on a polynomial. Extrema can be a global maximum, which is the highest point in the whole range, or a local maximum, which is the highest output value around that x value. Let's talk about it more. So the output value at the highest or lowest point. So this is output value at the highest or lowest point of the graph in the neighborhood of a value, or in the domain, in the neighborhood, or let's just say domain. The output value at the highest or lowest point on the graph in the domain, that's what you call your local extrema. The idea is that so this point is going to be my local minimum, this point is going to be my local maximum, because it is the highest. This is the highest point around this value 2, this x value 2, and this is the lowest point around the x value 3 point something. So that's going to be a local extrema. But when you come to global extrema, it has to be the output or the highest y value, the output at the highest or lowest point of the graph, right? This is going to be the highest or lowest point of the graph in the entire range, in the range. So that is going to be your global extrema. Just like you see in this picture, this is a global maximum, and this function doesn't have a global minimum because the function is continuing endlessly towards infinity, towards negative infinity. Intermediate value theorem. This is just something to expose you to. So the intermediate value theorem is simply the idea that if you have a function, if you know two values of a function, if you know, for example, for this function, if I know what f of a is and I know what f of b is, then common sense just tells me that this function has a value between a and b, right? It definitely has a value between a and b because it has a value at a and it has a value at b. It's just like saying if Mr. William was 10 years old at some point in his life and he's now 40 years old at this point in his life, then he definitely must have been 12 or 16 or 20 or 30. He definitely must have been those ages because we have these two endpoints. So if a function has two values, f of a and f of b, where a is smaller than b, then that function must have a value between those two. And really that's what the intermediate value theorem talks about. So this fancy language, if f is what do you think can fill in this blank on a and b, and k is any y value between f of a and f of b, then there's at least one x value between one x value c between a and b such that f of c is equal to k. There could be at least one, but there's infinitely many values between two endpoints on a function, not endpoints, two values on a function. So yeah, find a suitable word to fill this in to show that you've understood that idea. Another way to state it is if f of a and f of b have, what do you think, opposite signs. So if they have opposite signs, this is a mathematical way to put it. If they have opposite signs, then f of c has to be equal to 0 for some number c in the interval a and b. What does that mean? If using this graph here, this is f of a is negative, this is f of b, it's positive. If the signs of these two are opposite, if one is positive and the other negative, then surely there must be a value of the function where that function touches the x-axis. The idea is simply that if you have a function and you have two values on the function, a positive value and a negative value, then that function must cut the x-axis in between those two values. In between, so if this is a, the x value is a, and this, the x value is b, then the intermediate value theorem says that the function must have a 0 in between those two values if the output values of the function for those input values are opposite signs. So an example is here: use the intermediate value theorem to confirm that the given polynomial has at least one 0 with the given interval. So in order for us to check that, we'll just look for g of -4, find the answer, and then look for g of -2, find the answer. If they are opposite, that is enough proof that there is a 0. So if I'm doing -4, it's going to be -4 cubed minus 9 times -4, which is 64 plus 36, which is some number, sorry, -64 plus 36, which is negative something, and this is -2 cubed minus 9 times -2, which is -8 plus 18. This is a positive 10. I can see this is a positive and this is a negative. Whatever the answer is, it's going to be negative. So that's enough proof for me that this polynomial has at least one 0 or one x-intercept between x values of 4 and -2. Right, our last example, an open top box is to be constructed by cutting out squares from each corner of a 14 by 20 sheet of plastic, then folding up the sides. You guys have probably done this in 6th grade, where you cut out the edges of a square and then make it into a 3D box. Express the volume as a function of the width. So if this is x and this is also x, the width was initially 14 and the length was initially 20. So from the width, they're cutting out two x's because they're cutting out this x and they're also cutting out that x. And from the length, they're also cutting out this x and that x. So the new dimensions are, the length is its initial 20 but minus the 2w, and the width, the new dimensions are its initial 14 minus the 2w. Now you know that the volume of a cuboid or a box is length times width times height. So I'll have length, which is 20 minus w, times width, which is 14, sorry, this was 2w, 14 minus 2w times the height, which is w. I hope you can see that when you fold this, sorry, not w, the height would be x. I don't know why I've been using w, but this should have been x the whole time, because x is what's being cut out. X, sorry about that, x. Okay, so when I expand this out, let me start by expanding these two. 20 times 14, I do not know what is 20 times 14. Calculator. 20 times 14, 280. Okay, so that's 280. 20 times 2x is 40x. 20, yeah, finished. Negative 2x times 14 is negative 28x. Negative 2x times negative 2x is positive 4x squared. All of this is being multiplied by x. So I'll have 280x minus 40 minus negative 40 minus 28 is negative 68 times x is negative 68x squared, and plus 4x squared times x is 4x cubed. So this is the expression for the volume of the box as a function of the width, which is x. Right, next question is find the size of the squares that should be cut out to maximize the volume enclosed by the box. So going back to this expression of the volume where it was not yet factored, 20 minus 2x and 14 minus 2x. 20 minus 2x, 14 minus 2x times x. This is an expression of a polynomial function. If I solve it, if I try to equate each of the parentheses to 0, my zeros or my x-intercepts will be x equals 0. That one is coming from this one. Then if I equate this one, this bracket to 0, I'll have 20x. 20 is equal to 2x, which x is equal to 10. And then from this parenthesis, I'll have x is equal to 7 because I'm equating each of them to 0. So remember, x is the width of the box. So this 0 of x is equal to 0 and x-intercept, I cannot have a width of a box that's equal to 0. So that's not realistic, so I'm going to discard that one. Then I have x is equal to 10 or x is equal to 7. X is equal to 10, it's not going to be possible because the dimensions of this are 14 centimeters by 20, right? Those are the dimensions, 14 by 20. So if the values that I'm cutting out are the values of x that I could cut out of this box, could be 10 or 7, and remember I'm cutting out twice of each from each side. If I cut out twice of this from the width, I'll run out of width because the width is 14 and twice of this is already 20. So this value is also not going to be realistic for this model. Let me explain that again. The width of the box before I cut it was just 14 centimeters. Now if I'm cutting out a value of x is equal to 10, and remember I'm cutting out 2 x's from each side, there's no way that I can cut out 20 from 14. I'll have run out of space. So this value also, this 0, is also not going to be realistic. So the only 0 that's going to be realistic for this problem is x is equal to 7. So when the question asks find the size of the squares that should be cut out to maximize the volume enclosed by the box, my answer is going to be, the size is going to be 7 centimeters, because fortunately it's the only realistic one for this problem. What is the maximum volume enclosed by the box? To solve that problem, I would have to graph my function. I would have to graph the equation of the volume. So what I did is just to graph this. When I graphed this on a graphing calculator, it gave me this expression. And on this expression, since I'm only interested in the value of x that is 7, I'm also going to be interested only in the region on the x-axis between 0 and 7, right? That's the region that I'm going to be interested in, because the y on this the y values on this graph represent volume, and the x values on this graph represent the distance that's cut out. So the only realistic values for this volume, for the maximum volume, will only exist between 0 and 7, and I can say that in that region the maximum value for the volume is around 339. The maximum volume, the Vmax, is around 339, which is, we could say, 340 centimeters cubed, when it's happening at an x value of 2.7 centimeters. So if you want to maximize the volume, you're going to cut out distances of 2.7. All right.